Let's look closely at the flame of a candle. Can we get that on the screen? Okay, so the luminous part of the flame is forming above the wick. If we look closely, there's a beautiful blue area at the base of the flame. Can we maybe darken the image slightly? Maybe a little bit more. And as we do that, the camera, it begins to see what we can already see with our eyes, that the center of the flame is darker. In fact, the flame is hollow. We can see, I think, maybe brighten it slightly, we can see that the wick is curved and the end of the wick is projecting out to the edge of the luminous part of the flame. So we've begun to see more about the flame. A question: how does the wax from the candle get into the flame? It goes through the wick as a melted liquid, and it travels up the wick by a process of capillary attraction. And we can demonstrate that sitting at a meal table, perhaps. I like dinner table experiments. If your children do this at the meal table, of course, this is called messing about. If we do it, it is, of course, experimenting. Can we get that on the... I think everybody can see. Okay. I'm intrigued by Faraday's mention of this discovery made by the late Duke of Sussex involving washing a prawn. And I thought, if this hasn't been done for over a century, maybe we really ought to try it. Let's move this. So let's go. Obviously, the initial dripping has caused the water that's already in the prawn, but I think we're going to see that they continue to drip until the level of water in the glass drops sufficiently for them to stop. So that, ladies and gentlemen, is how we wash a prawn. And I think it's distinctly possible that nobody's seen that effect for over a century. I'm not really a proper scientist. I have to confess that to you tonight. My work involves engaging young people's minds with real natural phenomena. And somebody asked me earlier this evening, over a drink, how one tells what will appeal to young people and what will not. And that's a really interesting question. And really, it's what I've been devoting my working life to for quite a number of years now. And I like to think that the flame that we've just lit here, literally, is a nice metaphor for the lighting of the flame in young minds. And I want to show you, as well as showing you natural phenomena, physical phenomena, I want to show you some examples of young people actually interacting with natural phenomena in a way that is palpably like a flame being lit. I'd like to show you a short video clip taken a long time ago, in 1992, in a science centre which I designed in Liverpool. Sadly, it's no longer there. It didn't last very long. It was funded by a commercial leisure company, which subsequently went insolvent due to other projects, not that project. Very unfortunate. But let's have a look and just see. Great Explorations is a hands-on science centre. Nobody says don't touch. It features interactive exhibits, things that are simple but carefully designed. They're found fascinating and thought-provoking by everyone, from infants to adults. Children and adults enjoy them together, but the children are in charge of the experience. Primary schools are benefiting particularly, from 11-year-olds right down to 5-year-olds. There's such breadth of appeal here, though, that secondary schools can benefit very much as well. Because it's designed to complement and inspire more formal classroom learning afterwards, there's no conflict here between education and enjoyment. But Great Explorations is not a classroom. This has to be emphasised. An hour or two in Great Explorations is not intended to convey all the knowledge and understanding of national curriculum science, but it is more than enough to motivate endless follow-up work and inspire long-lasting enthusiasm and interest. This place really is all about exploration. It legitimises our precious freedom to investigate things for ourselves, driven purely by our own curiosity and excitement, without being overawed, intimidated or browbeaten. Historically, this has always been the real essence of true science, and it's also National Curriculum Attainment Target number 1. This freedom to explore exists within a detailed and carefully structured learning environment. The intrinsic appeal of well-presented natural phenomena is not only useful in what we've come to know as a science centre environment like that, but places like Daresbury Laboratory in Warrington, for example, I've done a lot of work for them over the years, producing exhibits for their science centre, which is used by local schools. It's very popular with local schools who visit, and they have their own agenda, but the agenda of Daresbury Laboratory very much is to establish community relations and to communicate the nature of their work to the wider public. And being able to offer experiences which engage people in a way that they really enjoy and want to come and see is very important to them. And this summer I produced this display for the Royal Society Summer Science Exhibition after long discussions with a Cambridge research team working on the genetics of Alzheimer's disease using fruit flies. And this was a subject that they wanted to communicate to a very mixed audience with quite a lot of young people, family groups, school groups, as well as professional scientists, in a way that engaged and appealed and informed. And so we came up with ways of doing that. Well, I think this is a very important picture. Have you ever noticed that kittens are obsessed with physics? Right? Kittens are genetically programmed to learn and to research Newton's laws of mousing. And this is natural learning, and this is very important, but natural learning looks like play. Okay? I'd just like to bear that in mind, because there have been various comments made about the behaviour that's observed in young people in science centres, and people say, but they're only playing. They're not only playing. It's much more than that. Okay, back to the candle. Here's a really nice party trick. Where's my lighter gone? I did have a lighter there. Can you pass me that one, Andrew, please? That'll do fine. Yeah, that's fine. Thank you. Cheers. Let me just do this. Yes, let's move. Yes, we'll do it with this candle. Yeah. Did you see that? Watch. I can only do this so often because as the wax cools, it's giving off less of that dense white inflammable vapor. But that's a nice trick. And in order to do it, we have to be quick and ready, as Faraday said, because if we don't ignite the flame at just the right moment, we miss our opportunity. And I'm really stretching my metaphors this evening, but I want to make the important point that communicating science to young people is actually seizing the moment and communicating to an extremely receptive audience. Again, in conversation earlier this evening, it's been commented to me that speaking to teenage children, for example, is a lot more difficult and less rewarding in many ways than speaking to younger children. So we mustn't overlook the opportunity we have to communicate science at really quite a young age, under the age of, say, 12. Primary school children seem particularly receptive to natural phenomena. And again, I'm remembering the behaviour of the kitten with the ball of wool. This is, exploding custard is something I've become trapped in performing. It's my children's science show, my kitchen table science experiments, which I originally developed back in 1990, I think it was, for the Edinburgh Science Festival. I suggested to them that maybe they could do something which was a little more informal, a little more likely to attract wider age ranges. And they said, well, what would you call it? And I said, well, I had this vague idea that corn flour could be made to flash. And I said, well, maybe exploding custard. And they said, well, come back next year and do it. As I then had to figure out, I had to prepare a show and do it. And I was quite nervous for the first couple of years, but it was, I've been doing it ever since, and audiences won't let me stop. It's very, very popular. And I'll show you some pictures later. But basically, that's a photograph of the Kraft General Foods custard powder factory in Banbury in Oxfordshire, which was totally destroyed by exploding custard in 1981. I actually wrote to Kraft General Foods, to Bird's Custard, hoping they'd sponsor me, but I got a they didn't want to. I got a very amusing letter back, which I've kept, telling me that I was to stop immediately because I was raising public concern about the safety of their product. So exploding custard is one of my science shows. My other one, I developed a biological one. I tried to think of a name that would match. It's a show where I link a video camera with microscope, and I show living microscopic pond life. And that one's called Blown Up Biology. And this is what an audience can look like. This is a scary audience. I'm quite relieved that you're not quite such a scary audience as I feared, actually, tonight. But this is a Swiss audience. And last summer, I was invited by Remo Bezio, the director of the excellent science centre in Winterthur in Switzerland, to go there for over a week and do 2 shows a day of my exploding custard show, or Der Exploder and Der Pudding, as it was called. And so I went through the script with him before we started, and I was saying, well, at this point the audience will be cheering and clapping, and at this point they'll be doing this loud countdown. And he said, oh, no, they won't. He says, this is a Switzerland. They will just sit there. And I began to think, well, I'm going to have to, really adapt to my audience. And I do like a challenge. And I noticed this photograph. A photographer came in, a very good professional photographer came into one of my shows, and he photographed me and he photographed the audience, and they do look rather scary, don't they? And this was at the beginning of the show. So I used various techniques to try and win them over and loosen them up a little bit. My German's pretty appalling, so I used PowerPoint to help me. But one technique I used was to ask them questions. I would invite them to predict the outcome of an experiment. And this is very successul with children and with mixed audiences. You get them to vote. How many people think this will happen? How many people? Basically, this one is what's happening there. There's a spoon suspended from a balance, and I'm going to bring the water up under the spoon, and they've got to predict if the spoon will stay still, go down, or go up. And in fact, most people I know from experience actually know that the spoon will move up. So this is like educational research. I learned quite a lot from doing this. The other one I do is to hang a bucket in the balance and dip my finger in, and they have to predict if the bucket will move, if the bucket will stay still, go up, or go down if you just dip your finger in the water. And I'm not going to tell you the answer. Because telling you the answer actually stops you from thinking, and that's something else I've discovered. So, releasing a screaming balloon rocket over their heads, that worked quite well. But then, and of course I'm talking about the forces involved and what's actually happening there in terms of physics, but that was with air, and then I say it's much better with water. And this is, I don't know if you're familiar with the wonderful water rocket kits, which convert a 2-litre plastic bottle into a 100 miles per hour projectile. and doing this indoors is really quite scary, yes. So, but I hit on the idea of running it along a braided nylon cord attached to the wall, right at the back of the lecture theatre, with a big, solid, very strong foam pad. And it really did work very well in two senses. It worked very well physically, and it worked extremely well in terms of the audience's emotional reaction. So there I am pumping it up, telling the children not to stand up. And there it goes. And it's travelling at 100 miles an hour, and the audience, if you look at the photograph, it's interesting, they're all looking at the point of departure. None of them are looking at the rocket. It's going so fast. He was a good photographer. And of course it thumped into the padding at the back of the lecture theatre, then slid back down with this wonderful condensation cloud inside it, which I was able to puff out through the neck of the bottle. And just look at the audience's faces now. That's the same audience that you saw at the beginning. And if you like, this is the flame. This is the igniting of some kind of response to exposure to a really appealing physical phenomenon. And here we're preparing to explode some custard. And you'll notice that I have the same apparatus here. And I'm saying, shall I put a little bit more in? And some of them are shouting, "Ya," and some of them are shouting, "9." And the ones at the back are shouting, "Ya," and the ones at the front are shouting, "9." And I point this out to them, and then, of course, they're shouting even louder. And this is the Swiss audience that wasn't going to respond. And then we have a countdown, 10, 9, 8, 7, and then we explode the custard. And you'd really like to see me do that, wouldn't you? Yeah. Oh, this is a great audience. And of course, so we're going to do it at the end. Ah, everyone says. Okay, changing people's perceptions. Let's, Andrew, can we look at the shadow of the flame? Shall we look at this one? This is easier to see in bright sunlight. We need a small, a narrow light source, and of course the sun being far away has that effect. Very often, the interesting thing about seeing this sort of thing in a formal context where I'm legitimizing the experience for you, I'm saying, look, it's legitimate to look at this sort of thing and think about it. Kids will go away, adults will go away, and they'll notice things like that. If you're sitting in a warm heated room in the winter, the windows open slightly and the sun's shining, you'll see the shadow of the warm air streaming out through the window, making patterns like that. It's interesting that the darkest part of the shadow is the brightest part of the flame. Can you see? You can see the flame in a different way. And having seen something familiar from a different angle, a different perspective, you'll never see that thing the same again afterwards. We extend our vocabulary of experiences. I'm trying to point out that not all learning consists of just the sorts of things that you need to pass an examination with. Okay, thank you, Andrew. That's brilliant. Okay, now let's try something else with the flame. Here's another experiment. Which flame shall I use? I think I'll use... Oh, gosh, that's stuck to the tablecloth. Sorry. I have to be very careful. I've got a bucket of water here in case I do this wrongly. You would never, nowadays, with health and safety rules being as they are, do a show like this for kids, would you? I'm trying to show, can you see there's a ring there? Okay. Let's do it again while we're switching over. Pause and back. Yes. Can you see that? 2 eyes. Okay. Okay, and there's the real thing. I don't know whether to show it to you or to show it to the camera. Okay, so that's happened because the candle flame actually is not quite as we think. It's actually hollow. We think of that as a solid mass of luminosity, but in fact it's a hollow shell inside. It's full of gas. The outside, where it's meeting the air, it's luminous. And that's revealed that to us. So now, hopefully, again, you won't think of a candle flame in quite the same way. Let's look. Yes, can we try looking at this flame again and see if we can show the blue part of the flame really clearly? Just try and set the light so we see the blue part of the flame. We got that? Yes, we can just about see that. It's interesting that the human eye, I can actually see the dark part of the flame and the blue part simultaneously, but the camera has to be adjusted to see one or the other. But next time you're sitting in front of a candle at a dinner table, look at it closely, and you will see that. Having had it pointed out to you, you'll see it again in everyday life. But what is the oxygen that supports children's learning enthusiasm for really good science centre stuff? Think about that question while we watch the next video clip. Because of the motivating emphasis on exploration, there's no need for adults to feel anxious on account of any lack in their own scientific knowledge. Great Explorations simply isn't an intimidating place. Here is a very important point. True exploration is encouraged more by open-ended questions than by pre-packaged explanations. And children find questions more convincingly open-ended when they're asked by an adult who does not necessarily appear to know the answer already. Here, children are particularly encouraged by adults who are prepared to listen to them. Great Explorations is clearly an opportunity to correct the masculine image of science. Cooperation is very important, and there are plenty of opportunities here. The exhibits are designed especially to allow a number of children to use them at the same time. Great Explorations crew members wear distinctive blue and yellow uniforms. Just like good, supportive teachers, they share the process of discovery with the children. They're not there just to convey information. Groups of children can be seen discussing their shared experiences. Okay, so, I recorded that in 1992, a long time ago. I've done a lot more Science Centre work since then. That was one of the very first handful of Science Centres in Britain. As I say, it's sad that it's no longer there. The exhibits have recently, some of the ones that have survived, have ended up at the Kelham Island Museum in Sheffield recently. But what I was suggesting there was that exploration is a key thing. And nothing that's happened in the intervening years has changed my mind about that. As a designer of these experiences, I produce interactive exhibitions and exhibits. I need to get it right. There's a lot of talk about evaluation studies and so on, but really, it's an art. It's an art. You have to be able to predict what the children will respond to and how they will respond. And experience really does help there. And a rule that I just find myself following is to ask myself, will this promote exploratory behaviour? And if you ask me what exploratory behaviour is, I hope you've seen some examples of it in these short video clips, and I'll show you an even better example shortly. But rather than try to define it, I'm not an academic. I'm just somebody who survives commercially by practically getting it right and knowing what appeals and what works educationally. And somehow there seems to be a kind of spark in a group of people where they are exploring things, they're discussing ideas, they're trying something, and you can see them thinking, and then they try something else. That kind of response there is something very important going on. I find it very hard to define in words. Maybe it's like a new science where we haven't invented the vocabulary yet. We're at the phlogiston stage of understanding this particular flame, perhaps, this electrical fluid. But exploratory behaviour is important. And we need to provide opportunities for it. We need to give people freedom to explore these experiences. And especially importantly, we need to encourage them to explore experiences like this. These are principles that I find myself following in my work, and they seem to work. That's all I can say. We live in a culture where education is seen as being something increasingly involving sort of attainment target box ticking and examination passing and so on. And these things are clearly important, but if we can motivate people before, I have a personal saying that if I give you facts, I feed your mind for an hour. If I awaken your curiosity, you feed your own mind for the rest of your life. And this is the kind of thing which Science Centre work seems to achieve. And when it's evaluated against the standards of purely cognitive learning, very often the results can be disappointing. Okay, back to the flame. Let's see if we can get this working. This is slightly tricky. Andrew and I struggled with this earlier, but we did get it working. And it's one of Faraday's experiments, and it showed how clever he was, because when you try and do it, I'm going to try and extract some of the hot waxy vapour from the centre of the flame and draw it out through this glass tube, and if we're really lucky, maybe ignite it. Many of us have seen the textbook diagrams, but actually doing it is never quite so simple. That's a little bit too high. I'm going to drop it down a little bit to there. Can you see? I can see a white vapour coming out the tube. Right. There we go. Now the next trick is going to be trying to light it. I don't know if there's enough. There isn't enough. It's not going to work, Andrew. Well, if I hold the flame there, you can see there's something going on. Will that do? Can you see? It's trying to burn. I'm not going to labour this, but... Okay. The flame needs fuel. And the fuel that's burning in the flame is this wax vapour. So it's actually a gas flame, in a sense. Maybe I could just try again. Oh, nearly. No, I'm going to give up. Lots of things we see in textbooks are, we're very familiar with them, but actually trying to do them can be quite difficult. The flame needs a balanced mixture of fuel and oxygen. So let's imagine we've got an oversized wick burning an inflammable fluid, in this case white spirit. And see what kind of flame we get. Because the wick is large, the amount of oxygen that can reach it while it's burning is proportionally less. There we are, we're making rather a lot of sooty smoke. And so I won't prolong this, I'll drop it into a bucket of water. Right, now, any candles burning everywhere. Let's light another candle and watch the wick. because the interesting thing about the way a candle's wick works is that it regulates its own length. Can you get that? Okay. Now this is a new candle. The wick is too long, and let's see what happens to it. Have you got the brightness now? I can't see. Okay. Watch the wick. Can you see it's shortening? The exposed, oh, yes, that's it. The exposed part of the wick, exposed to the atmospheric oxygen, quickly burnt away. And the wick has bent over, and it's just peeping out at the side of the flame. The wick in the candle never seems to be vertical. It's always bending off to one side. And where it sticks out the side of the flame, it burns away. And so it regulates its length, because if the wick is too long, we get a smoky flame, like we just saw with the white spirit. So that's an interesting thing about a candle, because very often we see sort of cartoon sort of pictures of candles, and the wick's straight in the middle, and it never is in reality. The wick is always bending out and sticking out at the side. That's not an accident. It's the way a candle works. This balanced, thanks Andrew, that's brilliant. The balanced mixture of fuel and oxygen, I'm going to draw that into my metaphor as well. I'd like to suggest that explanation is like the fuel and exploration is like the oxygen. Okay? And I know I may be labouring this, but I want to make the point that, again, in my work as a science-centred designer, I find myself constantly having to balance the essential need for sufficient explanation in a presentation with the equally essential need to encourage and permit exploration. And you can't really have a lot of explanation and at the same time have a lot of exploration, because if you explain everything, you don't leave anything open to explore, and if you leave everything open to explore, well, you haven't explained enough, maybe. So it's a creative tension, which I find really, again, very prominent in the thinking that I have to do with almost every project. And it's quite controversial, because when hands-on science first started in this country, the idea seemed to come from America, from Frank Oppenheimer's Exploratorium Science Center in San Francisco, which had been going a long time. And it was a wonderful place, and I remember the wonder of thinking, what a brilliant idea. And they were presenting phenomena directly, in a non-intimidating way, not too much explanation, all this kind of thing. No fancy design, everything was just done by ponytailed San Francisco people with, welding gear. And if you wanted to adjust an exhibit, you did it with a hacksaw, all that kind of thing. And it started off in this country like that, but it's changed. And many new science centres have moved a little bit further towards the explanatory side. And I'm just a little bit concerned about that, because I don't like the idea of dismissing old-fashioned science centres as exploratory type science centres which just present phenomena and don't explain enough and all that kind of thing. We're constantly seeking this balance, but we mustn't explain everything. It stops people thinking, and it destroys the opportunity for exploration. I'll maybe say more about that later. Here's an example of a very simple science centre exhibit where you have three coloured spotlights in primary colours, red, green and blue. And if they're arranged in a triangular arrangement, when you look at the shadow that they cast, where the coloured lights overlap, we get some really interesting effects. We get yellow appearing for a start. Well, where's that yellow come from? We've only got red, green and blue spotlights. Well, I'll leave you to think about that. But you see the way I've held my hand there, I've made a little hole with my fingers, and we can see, and a laser pointer, you can see the classical textbook colour diagram with the white in the centre, the red, green and blue primaries on the outside, and you can see the cyan, yellow and magenta colours inside. All very interesting, and that can all be explained and talked about. But look at the response of this extremely small child that I photographed in Technorama last summer. She was quite oblivious of everybody. She'd wandered away a short distance away from her parents, and she was just in her own little world, little private world of experience and emotion. She stayed there really for some time. And somebody could have gone over there and said, well, she's just messing about. That she needs to have it explained to her. Well, for a start, a child that age is really going to struggle with colour theory. I mean, I struggle with colour theory, you know. And it would be such a shame to interrupt that experience that she's having. And she's adding to her vocabulary of experiences, I believe. Here's another photograph taken in Technorama last summer. It's a classical Science Centre exhibit. I'm not sure if Launchpad in Science Museum in London still has theirs. Health and safety, you know, the kids can put their hands in detergent now. Of course, they can get it in their eyes. But you pull a string and you pull up a bar impregnated with detergent solution, and you produce this large, flat soap film. And it's illuminated in a very clever way. There's a white wall behind where those boys are sitting, and there's a black wall behind the soap film. And so you get a black background with a white surface reflected in the soap film, and you get the most beautiful interference colours. And of course you can blow on the soap film from quite a distance and get beautiful patterns, beautiful effects. Absolutely stunning. I've never seen computer graphics that could match the patterns and the dynamic sort of shapes that you see in that. Now those two boys are sitting. They've provided, the designers of this excellent exhibit have provided a seat, which is a really good way of getting people to focus and concentrate. But I'd like you to try a little thought experiment now. There's an empty space on that bench next to the boys. I'd like you to just picture a teacher, a physics teacher, a very earnest, enthusiastic physics teacher, walking up into the scene now. Just conduct this thought experiment now privately, each of you, and imagine the teacher sitting down there next to the boys. What's the teacher going to do? Or probably going to start explaining what's happening. And the boys are going to politely listen, for as long, depending on how polite they are. But I have seen this many times, and what they will do, as quickly as possible, is they will detach themselves and walk away and find something else to do. That's just my experience. I'm not going to analyse it any further, but that happens quite often. Here's another nice Technorama phenomenon-based exhibit. It's actually in the context of an exhibition on mathematics. It's a lovely thing. There's sheets of flexible plastic, I think it's polycarbonate, with a blue liquid between them, and you can pull up on those four knobs that you can see, those dark shadows, and you can pull up and suddenly it goes and separates, and air sort of shoots in to the liquid, and it produces this beautiful fractal pattern. And it's, as a context is important, it's presented in the context of a mathematics exhibition. And it's found extremely appealing by people singly and in groups. Here's a photograph of TechniQuest. And I'm very pleased to have as my guest tonight Colin Johnson, who until recently was the Chief Executive Officer of TechniQuest, the Science Centre in Cardiff. It's one of the first science centres in Britain, and it's what I would call a proper phenomenological, exploratory type science centre where visitors are at liberty and greatly encouraged to interact with many, many really interesting, real, natural phenomena. There are a couple of other science centres in Britain that like this, not many now. Launchpad, the original interactive gallery in the London Science Museum, is again this kind of experience. It's very interesting to go to Launchpad actually in the Science Museum because it's now in the basement of the new Welcome Wing, where above it there are galleries which are excellent but more explanatory, I suggest, and less popular. More people in Launchpad. I don't want to get too controversial, so I'll move rapidly on. But many Millennium projects now have moved more towards the explanatory side. And I'm just a little bit concerned about that. One of the indicators of losing contact with young people is a reduction in repeat visits, and statistics are able to demonstrate this. I'm becoming increasingly interested in small projects, and I've brought with me, they're in the library, a couple of miniature, mini-interactive exhibits which I've produced. There are two on turbulence, and they're on display in the library. Maybe some of you have seen them already. And my little mini-interactives are in use all over the place now. There's some children in Hong Kong, in the British Council offices in Hong Kong playing there. They've been touring around in flight cases in Hong Kong schools. And recently I've supplied a set to the New Science Centre in Johannesburg, and there they are in use by Johannesburg teenagers. So do have a look at my mini-interactives afterwards. Again, you're engaging directly with a rather beautiful phenomenon, turbulence, and you're seeing it from two different perspectives. One, you're rolling a marble round, and the other one, you're actually rotating a dome. And the water contains fine powdered mica particles, which makes the flow visible. Okay, back to the flame. Now let's set fire to some gunpowder. This is stuck to the candle tablecloth again. It rather amuses me that Faraday didn't actually forbid his juvenile audience from experimenting with gunpowder. He just sort of told them to do it carefully. And times have changed. But, don't try this at home. The full nozzle worth is a 12-bore shotgun charge, so you can see we've not put very much there. Okay. So we're going to see a flame. The brightness of this flame is largely due to the incandescent carbon particles which are going up in smoke. Here we go. Well, that's interesting, isn't it? Should we just... I have kept my powder dry. Yeah, okay. Let's do it again. But this time, we'll add some iron filings. And just demonstrating the principle that incandescence can be, of a flame, can be related to, let's put a bit more in, can be related to the particles, the behavior of the particles in the flame. This looks very like a firework when this goes up. I'll mix it with my finger. Oh, we've blown the... Just give the prawns a surprise. Oh, that was it. Okay. Thank you. I can smell burning hairs on the back of my hand as well. Right, so we've demonstrated that the point that the incandescence of the flame is related to hot particles. Going back to exploding custard, Faraday then he flashed some lycopodium powder. Well, in line with my principle of not doing experiments where possible, which you can't repeat at home on the kitchen table, I'm going to do the same thing with corn flour. I'm going to blow a very small quantity of corn flour through this flame, just to demonstrate what happened to the custard factory. Okay. Do you want to dim the lights maybe a little bit? Yeah, extra effect. Listen to the sound this makes. It made a much louder sound in the custard factory. that was about an inch worth inside a drinking straw, and we're going to put 2 teaspoonfuls in there afterwards. Right, well, remember when we blew the flame out before and reignited it, we saw white smoke. Let's do this again, and this time I'm going to raise the height of the tube a little bit and see if we can show you black smoke. Oh, wrong one. I'm doing. Let's hope this works a little bit better. Yes, card there. I need to turn this round. Ooh. It's a bit too high, maybe. It's hard enough doing this without 300 people watching you, of course. Yeah. There it goes. Can you see there's a slight draft? Okay. Up. How's that? Have we got that? Okay. So by raising the height of the tube, the smoke coming out of the end has changed from white waxy vapor to black carbon particles. And another party trick is to do this. Now, if I spread my fingers and move them across the flame, I can do it fairly slowly because it looks slow because each finger is passing across the flame only just for a moment. But let's see. That doesn't hurt. And look, I cooled the flame. My cool skin cooled the flame, and the black carbon has condensed on my skin. So, again, what's actually happening in that bright part of the flame is that there's a lot of dark soot particles glowing. To catch up with this. So the bright flames contain solid particles, and really stretching my metaphors again, it's solid, real phenomena, I think, which are responsible for a great deal of the brightness of the flame that we see burning in these young people interacting in science centre type experiences. Now I'm going to show you a short video clip which I filmed in Technorama last summer, Technorama in Winterthur in Switzerland. I filmed it with a very small digital still camera, but I managed to get it taking movies, and I captured, it's very poor quality video, and I apologise for that, but it's a photograph, it's a video of another family using this exhibit, and it's a wonderful exhibit. I've never seen it anywhere else. It's the size of a snooker table, and flush with the surface is a fairly rapidly rotating stainless steel disc. It's spinning, as far as I could judge, about twice a second, and the edge of the disc is flush with the table. And on the table there's a selection of snooker balls, rings, several wooden ramps to roll things down onto the rotating disc, and there are some, you can see the child at the very back holding one of the balls, which has had a cylindrical section cut out of the middle. So it's a ball that's made into a ring, if you can picture that. It's a spherical shape with a cylindrical cutout in the middle. And you're going to see, I'm going to show you this video clip twice actually, because I think there's so much to watch in it. First of all, at the level of physics, you can see some really, really remarkable things happening as these objects behave on the rotating disc. But on a completely different level, you can see some extremely remarkable things happening, I think, with the family that's interacting with it. very much at the heart of what I'm really wanting to show tonight is this phenomenon. Because what is happening there? There's something, I believe, educationally very precious happening there, but I don't understand what it is. I'm unable to analyse it. But my job involves sort of designing experiences like this which produce exploratory behaviour like that. That's what I call exploratory behaviour. Let's watch it again, because it's just so nice. The same exhibit, on another day, I saw two, I think they were postgraduate physics students sitting on stools at one edge of the table. And it was funny because they weren't touching anything. They were just sitting there, not touching the objects. And various children and families kept coming and going around the exhibit. But these two, they were deep in discussion, with their hands on their chins like this, discussing in German what was going on. I couldn't follow what they were saying. I would have been interested to hear. But they were clearly analysing the physics. And there's a completely different level. Interactions were going on with small children. Really wonderful to see. Let's watch it again. Great. What are the results of the flame? Water. Let's where are we? Let's use this candle. I've got a syrup tin. I've got a jug of iced water. I'm going to hold the cooled metal above the flame and see if I can condense some water visibly for you to see. Stainless steel is no good for this because it doesn't conduct well enough. So the lid, yes, good idea. Thank you, Andrew. I think it fits. There's a dent in the tin. Oh, yes, I've got it in. There we are. Now then. I have to hold that like that, don't I? So I can, hang on, where are we? This is so hard to coordinate. Okay, tell me if this works. Did that mist over? Was that convincing? Okay. And there's a change in the gases above the candle as well. See, it's brighter now. Yes, there we go. That's slightly more convincing. We're getting carbon dioxide and water. So basically, above the flame, we've got soda water. The products of combustion. What results from the flame that I've been talking about in these people's minds? Well, attitude changes are taking place. They're seeing science in a different way. They may be deciding that they like science. The experience that they're enjoying is presented in the context of a scientific exhibition. You know, because we have an educational culture that doesn't necessarily emphasise as a necessary objective that children afterwards should decide that they like science, and that's important. They're seeing things which they will regard as legitimate to experiment with afterwards. That it won't just be messing about; it is actually experimenting, or it can be. I'm not the person, I'm not the academic to really analyse this, but I know that there are benefits there, and I just present the phenomenon to you for your consideration, and maybe for you to reflect on what benefits might be taking place in this encounter that we've looked at. Some benefits are delayed action, like a slow-burning fuse. A good example of this, I think, is the ray table. This is a very classical, very standard science centre exhibit where basically you project streaks of light, sometimes coloured light, across a white table, and you provide various lenses and prisms and mirrors and so on to interact with the beams of light and make them behave in different ways. A very appealing exhibit. It gets very interested, well-engaged groups of people around it, discussing and trying different things, exploratory behaviour again, and then they go away and think no more about it, perhaps. Years later, if they're children, they'll have their first optics lesson, where a teacher suddenly just draws mysterious boat-shaped objects on the blackboard. I can distinctly remember the first time a science teacher drew a boat on the screen and told me it was a lens. I could just see a boat, you know. I wasn't thinking in terms of a solid object. And seeing chalk lines representing light rays. Well, light doesn't look like a chalk line unless you've seen that experiment, unless you have that among your vocabulary of experiences. And that is so hard to demonstrate as a benefit, but I'm sure it must be real. Many of the most valuable benefits involve attitude changes, curiosity, self-confidence, motivation to learn. Children remember these experiences, real experiences on which teachers can build. Okay. I'm sure everyone's aware of this plaque in the entrance to the Royal Institution, commemorating possibly a demonstration lecture which achieved more than just communicate information and knowledge, but the inspirational dimension was important. Okay, very quickly, I'm getting a little bit tight for time. Let's quench the flame by taking away the heat, because a flame needs fuel, it needs oxygen, it also needs heat. Okay, I think. What's you going to? All right. Okay. Yes, that's right. Watch this. The black smoke coming above the flame. Okay, I've cooled the flame. The flame can't get through the gauze. The principle of the Davy lamp, of course. Okay, now do you want to lift the camera up and down? Because now this is a really, really nice way of showing that the flame is hollow. I just have to hold this steady. Can you see it? Isn't that nice? You can see right down into the flame. It really is hollow. You didn't believe me before, did you? And now you'll never see a candle flame the same again, because now you know it's hollow. Okay, thank you. I must move on. Okay, I must move rapidly on. I'm going to skip through this little bit where Faraday points out that basically each of us emits 7 ounces of carbon in the form of carbon dioxide, and that's what 7 ounces of carbon looks like. I'll make it exactly 4 charcoal briquettes. I haven't checked the calculation, but who am I to argue with Faraday? Okay, let's have a look at a really big flame. Let's experience the emotion and feel the heat. And I want a really good Royal Institution countdown. 2 teaspoonfuls of custard powder. That's a smallish helping of custard. And let's actually experience the calorific energy content of that. Where's my lighter? What have I done with my lighter? Got it here. Here, thank you. Sorry. I'm going over here. Bye, Colin. Okay, 5, 4, 3, 2, 1. Thank you. very much. Thank you. Thank you. Cheers. Thank you. Thank you. Okay.
Come. That's right.